streaming. What's up, YouTube? Okay, free bonus portion of lecture. I was talking to my first year college colloquia, and they had an option of 3 possible topics to end the semester, and they said, we don't want any of those, teach us how AI works. So I started live coding a computer vision framework, and I'm just going to show it to you because I think it was pretty cool. So I didn't know how computer vision worked, so I had to figure it out while I was going along. I think some of you have told this. I use the example of recognizing a die or a dice because you only need 3 by 3 pixels. So it's barely possible for your brain to hang on to this amount of information because you're 9 things, I can remember that. It's no, it's much more than 9 things, right? So we did a little talk on information representation. I was well, the die exists in 2 space, but really we're going to interpret the information in 1 space. Why are we going to do that? It is much easier to multiply a vector by something than a matrix by something. Okay, that was easy enough, right? And we said, well, how do we want to output it? Well, it's difficult for the computer to output 1, 2, 3, 4, 5, or 6. So what do we output instead? We output a feature vector. So we have a feature vector, which is a 6 by 1 vector. And there's zeros or ones in all of the positions. Do they have to be zeros or ones? No, actually we're just going to try and get the highest value in a certain position. So this thing has the highest value in position. What is that? That is index 2, but there's no zero-faced die. So we say there's 1, 2, 3. Okay, so we're going to output a feature in position 3 in response to there being 3 ones arranged along the die. And that's not how it's going to work. 3 die, right, one of these things, right? So that thing is the same thing as this thing, I just use zeros and ones, okay? So information representation. How am I going to solve this problem? Well, I'm going to go from a 9 by 1 to a 6 by 1, and I'm going to go through matrix multiplication. You all know matrix multiplication. Fun fact, if you just edit the Wikipedia page on matrix multiplication, it's just LaTeX in there, and you can put that LaTeX in your Guardo Markdown. So this is just literal, actual, plagiarized Wikipedia. I should probably cite it. I probably meant to. But I didn't have to figure out how to do a diagonal ellipses, which I have no idea how to do that in LaTeX, but someone on Wikipedia figured it out, right? So anyways, I implemented matrix multiplication, which you all know how to do, and by the way, you do not even remotely have to implement matrix multiplication, right? Because you can just do either of these things in Python, right? But it's important to explain what matrix multiplication is the first time you do this. Okay, so we rewrote our matrix multiplier. You can do it with or without vectorization. They were complaining about vectorization. They're like, why are you teaching us vectorization? It's like, you asked about AI, right? Never ask me anything if you don't want to know the answer. So then what are we going to do? Well, to go from the 1 by 9 to the 1 by 6, we're going to create a 9 by 6 matrix, and then we're going to multiply things together. If we fill it with zeros, of course, it just predicts everything as a 0, right? That's not really what we want to do. So I filled it with random values, and then it predicts random outputs. It has no sense of intelligence yet. This is random initialization of an artificial intelligence neural network thing, right? Whatever. Okay, then we try to do backpropagation. Now, to do backpropagation correctly, you have to do multivariable calculus, and I couldn't figure out how to solve this problem because I didn't want to do multivariable calculus. But we show some things that don't work. We show that by default, when you predict things, it doesn't work. But we can also see, if we're trying to predict that something is a 3, which is in the second position, everyone hates off by 1 errors, right? This was not ingratiating me to the first years. And say here's all of the different, and these are edge weights in a graph, by the way, but here's all of the different amounts that we add together to get something. Oh, this is also graph theory. I forgot, this is actually completely related to what we're doing in class. I just only noticed right now. Okay, so it said, here's one thing you can do. You can take all of the weights and reduce them, and then only increase the value of the weights that are predicting the thing you want. So what's this do? Basically, it causes this column to light up, right? So 466 goes to 931. Everything else gets smaller. 572 goes to 286. So what happens then? You're much more likely to predict things are 3. But the problem is you're predicting everything is 3. You're much more likely to predict anything is 3. And so if you check 5, you can do the same thing, but you can't optimize to predict things correctly. You can only be very likely to predict one value. So when you train all values, you end up predicting everything is 5. And that 5 is actually a 6, right? Why are we predicting 6? Because it's the last thing we trained on. So this is a disaster. And there's like no real grateful way to fix it. So how do I solve this problem? And this is how I closed out the semester on AI. I said, well, we also learned about symbolic computation. I don't know if you all know about symbolic computation. It's awesome. We use it in my security research group to see what values affect other values when I perform computation. We don't care what the result is. We care what the source of information is, right? So if we do this, instead of making a random matrix, what I did was I made a matrix that was all symbolic values. So I created a symbolic Python symbol for my matrix B, and I just named it after its row and column location, right? So this is what the matrix looks like. These are all symbolic values. They don't have any numerical value at all, right? It's just algebra. And it's algebra and vectors, so yes, we're doing linear algebra, right? You got me. I'm doing linear algebra. The next thing I was going to do is multivariable calculus, right? But we can do a simple naive matrix multiplication over this, where I can take, for example, whatever 1 is, which is this thing that's 4 zeros. And so how do I draw that? I don't know if you care about this, but I think it's cool, so I'm trying to. 4 1s, or 4 zeros, a 1, and then 4 zeros. And that's the same as if I have a dot in the middle of the die, right? Okay. So I take that, I multiply it, and what do I get? I get B40, B41, B42. What is this? B40, B41, B42. What is this? This is predicting that the output feature vector is going to be determined by whatever number I have here multiplied by only that 1. So this is the output feature vector. It is just the weights on that 1 dot in the middle. And then it gets more complicated because everything else has multiple dots, right? So what is this? B00 plus B80. Why is that? Because those are the 2 corners on the die, 0 and 8, the first and last element, right? And it would also be the other 2. I'm only predicting on 2 being a single orientation. So anyways, what you can do then is you just figure out which one of these values are correct, which is just one more multiplication. You take this matrix and you just multiply it by the identity matrix. You put high values in all of those, low values and everything else, and then you've trained a computer vision framework. And what do I mean by high values and low values? You have to use derivatives there. But anyways, this is how AI works. I'm teaching a class on AI next term, so I figured I should learn how it works. And it seems pretty cool so far. Okay, today we're doing something way cooler than that, which is dynamic programming, which didn't really fit on the side, so I called the slides dynamism, which is not at all what we're doing. We're doing dynamic programming. I had to call it something. Dynamic programming, folks, it's awesome. Like, this stuff is so cool. The amount of math that is going on under the hood in this is like, I don't understand it all. I've been working on trying to understand it for a few years. I don't really do this except for fun, so I don't understand it that well. I was not planning to teach you dynamic programming this term at all. I was sort of assuming someone taught it to you in algorithms class. That maybe is true, I don't know, but then I also realized I didn't require you to take algorithms, so it wouldn't really help if you were going to learn it in the future. And then the other thing I didn't realize is I thought the algorithms I was going to ask you to implement to do some of this version control stuff, you could just brute force them without dynamic programming. That is completely false. I tried to compute the Fibonacci numbers without dynamic programming, and it took like 45 minutes to get the 50th one. So that is totally impossible. So anyways, I'm moving things around to try and finish. I might have to reduce the scope of the final now, which is fine. That doesn't hurt anything. It's not even released yet. But I'm going to teach you dynamic programming today. On Wednesday, Jimmy's going to be here. Jimmy is the fiend that forced me to teach this class in Rust instead of C. So Jimmy will explain to you why you're all learning Rust. Because I will say after implementing dynamic programming in Rust, I was like, why am I doing this, right? So Jimmy will be here on Wednesday and stabilize our emotional state. We'll come back next week, and then we're going to start on the stack allocated heap, then the Merkle tree, and I think that's everything we need, but I'm going to sketch that out. Okay. Huge news, guest speaker Wednesday, person who actually likes Rust. Oh, yes. It is not only that Jimmy likes Rust. Jimmy is one of 2 people I've met that gets paid to write Rust. The other person's at Amazon and doesn't only do Rust. So there's only one person I know that had a job writing Rust and nothing else, and it was Jimmy. And there's more of these people every year. Why did I panic and switch all of my course materials to Rust? I convinced myself you're all going to be expected to know Rust by the time you graduate. Time will tell. Regard attendance as mandatory. I will ask Jimmy who showed up. I don't know why I'm telling the people that are here that. Today I'm going to do dynamic programming, which is not exactly the same thing as memoization, which is not exactly the same thing as caching, and we're going to do a little bit of graphs, but we're only going to do the graphs by accident. Background. Okay. We are in a systems programming class. I am constantly being asked to explain and defend what systems programming is. I'll draw something on the board. This is a rock. That's a lightning bolt. This is a rock with lightning in it. Call this the central processing unit, right? Physical phenomenon, materials and electricity. Okay. None of us want to think about that except the physicists that sit in the front row every day, right? Okay, so shout out your physicist. Thank a local physicist, right? You see a physicist, say thank you, right? So our ancestors, the electrical engineers, they managed to put a barrier here. But those electrical engineers, what were they doing? They were doing stuff like setting up power grids, right? They weren't trying to do computation. So the only thing they could do is they regarded this as a bunch of wires, right? So we have a wire that connects this thing, and then you've seen maybe these circuit diagrams where they're like, oh, it's a diode, right? And that is, so this is physics. This is the register transfer level, because these things are registers and they're transferring. Register transfer level. This is a description of where the lightning goes within the rock, but it does not care that it is lightning in a rock. It could be simulated. Absolutely no one wanted to deal with that, so they invented a programming language, and the first thing they invented was an assembly programming language. And so that looks like this. Commands with arguments. Rust is compiling down into something a little bit ahead of this, and then it's getting converted to see the same thing. Usually people that are working here, these are maybe like computer engineers. And this is electric eng. Okay. Everyone hated writing that, so they made 3 things. Well, they made 2 things, and then they made a 3rd thing by accident. There was a compiler, which is rustc or GCC. And then there was an operating system, which is only Linux. There is no other operating system, really. Basically, Linux is so much the operating system that when we refer to operating systems, we refer to things that can do what Linux also does. And why did they do that? Because on top of Rust C and Linux, people wanted to be able to run Microsoft Excel, which is the only piece of software that matters. And so these are the software people. We usually call them either devs or engineers. And then who are the people in here? They're not really just computer scientists, because computer scientists often do like abstract things like graph theory and scientific computing. So I've been using the term computer systems. The system is the thing that runs on the computer that makes it possible to run software. And so it's this like intermediate level. We're not connecting physics to Excel. We're not connecting hardware to Excel, but we are hardware aware. So everything that runs to keep the computer working and able to be used is sort of computer systems level. So Versus software, computer systems expand the functionality of computing hardware rather than solving an end-user problem. An operating system doesn't do something, it is. The internet doesn't do something, it is. And then compilers don't do something. They like take text and make programs, right? Like it's the program that does something, right? So a compiler is a tool that can produce software. It is not itself classically software. File systems and cloud services are interesting. My take, and I've been shopping this idea around, and I have gone to some other universities to talk about this, and I've looked at some other people. It looks to me like if I'm teaching undergraduate computer science, I should teach you three things. I should teach you how operating systems work, how web servers or another network service work, and by other network service, I just mean MapReduce. I mean a specific cloud algorithm. So either you implement a web server or you implement a network service. Nginx is like the most powerful web server in the world. It's responsible for roughly 30% of the internet traffic. And so it has like a similar level of importance as Linux, right? We don't see it because we're connecting to things that are running on the server, right? And then a compiler, that's slated for next spring, and that's to understand GCC. No one understands Rust-C, so I'm not going to teach you how Rust-C works, right? Now, are you going to like grow up and like spread your wings and fly out of Willamette? I'm straining my metaphor. When you leave here, are you going to go write an operating system? No, probably not, maybe. But you're highly likely to write something or do something that involves understanding how operating systems works. There's not really a strong evidentiary basis that there's a better way to understand operating systems, how they work, than to just write a minimal one of them. You can sort of study them at the periphery, and it's sort of non-obvious that it's working. So the line of thinking here is when we're doing computer systems, when we teach software, we like usually ask you to like make an app or something, right? When we teach computer systems, we should ask you to implement a system. So I am going to ask you to implement minimal systems on the way to implementing the big system. What is the minimal system? It is something that is interesting and useful and requires the same skills, but does not require thousands of lines of code. And so I've been looking around for examples of like little systems that are useful. The jump I'm always worried about is you finish data structures, and then I'm like, write an operating system. And you're like, there's like things in between there, right? Last year I made them implement a blockchain, and I was told that was cringe. So now we're trying source control management, SCM or VCS this term. It looks pretty cool, and this is going to help you understand a real important computer system, which is Git. Git is an important computer system. It is not as central to the universe as an operating system. People developed operating systems for decades before they invented Git. But it's pretty important. Am I streaming? Okay, hold on. We have to press some buttons. Okay, I'm going to turn off screen capture. I'm stressed out running this.
I maintain Git for...
Wait, what? Why is the sound not going through there? Wait, there's captions. Read the captions.
For 3 or 4 months. I think I handed it off in August or something like that. And when I handed it off, I truly just handed it off. I still feel silly. My eldest daughter went off to college. 2 months later, she sends this text to me and says that I'm more well known at the computer science lab for Git than for Linux. Because they actually use Git for everything there. Git was never a big thing for me. Yeah. It was I need to get this done to do the kernel. Sure. And it's kind of ridiculous that, yes, I used 4 months of my life maintaining it. But now, 20 years later, yes, you should definitely talk to Junio, not to me, because he's...
So, it is odd to me that it's like there's this person that exists historically. That's why there's an operating system that's free, right? There could have only been paid operating systems. And it's maybe going back this way. Harmony OS is like a big deal that's come out recently that's owned by Huawei, and it's closed source. Fuchsia, developed by Google, is like owned by Google. So there are now more operating systems coming online that will probably, in the fullness of time, compete with Linux. Windows really thought they could compete with Linux, and that was fake, right? When cloud technologies exploded, no one was running Windows on anything. It was completely unreasonable to pay the licensing fee, so Linux took over everything. In this interview, like the person that wrote the world's most important free operating system for free, which is just like a strange thing, right? Says, I had to get Git done so I could do the kernel. Do the kernel is not relevant to us right now. There was this missing computer system that made it impossible to do something else. And so everyone working on this team had to drop everything and invent Git quickly. And they did it in 4 months, and it's still around. That's an example of a computer system. The first operating systems that came out is like, I can't write print in every single piece of software I develop. And the first compilers that came out is, I need a programming language. I can't write everything in assembly. These are solving problems on the way to developing software, doing something else with a computer. Nominally, Git is pretty simple. I don't know if I think that's true, but you can look at the very first commit of Git, and so the first thing that Git maintained was itself. There's not that many lines here, and this is also not that old. Some of you are probably older than Git. One of the things I didn't know is like when in 2011, when I was being told to start using Git, it was like brand new and people didn't know it was going to be a thing yet. So like someone just made some lucky guesses. This is written in C because it's older than Rust. But there's not a lot of lines of code here. That's 25. What's this? 100 something, 250. This is like final project size. And that got me thinking about what the final project for this class should be, right? So I'm going to try and have you make, it doesn't have to be like Git. Obviously, like one of the best programmers in the universe worked on it for 4 months, right? But we can probably do a little bit. As far as I can tell, and I'm not really a good source on this, because I was going to do blockchain, right? And it's like, blockchain has like political problems, right? So what are we going to do instead? I think we're going to implement a source control management software. And the source control management uses SHA and ED25519, which is why I had you implement those. And it also uses something called a Merkle tree or a hash tree, which was going to be today. And we couldn't do it yet because we were missing one thing. The other thing it needs is a solution to the longest common subsequence problem, which was way harder than I thought. It was way harder in the sense that I was going to give it as the homework assignment last week, and I was like, that seems mean. So I'm going to teach a lecture on it, and it's actually going to be super easy after this lecture, I think. But I think it was worthwhile to have this lecture. So, how are we going to solve this? Least common subsequence is polynomial time complexity, big O of n to the x, right? And has an efficient algorithm to solve it. It is often employed to compare data and merge files, or merge changes to files in programs, such as the diff utility and revision control systems, such as Git. Have you all seen diff before? Why is that window open? That's weird. Let's get my screen back on. So, I mentioned I was teaching a little bit about AI earlier today. And unfortunately, I was live coding in Vim, so I completely cooked my file permissions, and I have no idea what was going on. So I made a backup version of my AI.qmd file called panic.qmd. And so that panic.qmd is a snapshot that occurred at some point while I was writing code, and I don't know exactly when. I'm not using version control here because I'm a bad teacher, right? But there's something that predates Git, and predates, in fact, the version control system before Git, which was called SVN, which Linus Torvalds regarded as unusable, and I regarded as totally fine the entire time I used it, so I don't actually even understand the problems with it. But I have AI.qmd, I have panic.qmd, roughly similar number of lines of code. We can look at the head of both. So those things look pretty similar. You see I'm citing Stack Overflow, right? So there might not be that many changes, right? And if there's not that many changes, what we can probably do is we can take a diff and see what the changes are. And what we find out is that there's relatively few lines of code that differ. I'm going to embiggenify this, and it'll look a little better, I think, but not that much better. AI.qmd, which is on this side. Left? Which side of the screen am I on? Am I on the left side? You're all just you're shaking your head left? Yes, okay, thank you. So this arrow points also to the left, and AI.qmd is on the left. So this line exists in AI.qmd, but not panic.qmd. So does this line. This is not its own line, right? That's the X in matrix. Empty line, and then a Python code block. And so it was, this is fast. How fast is this? So it did that in 0.003 seconds. And how long would it take to just cat the same thing? About the same. So it's as fast as reading both files, I guess. That's pretty fast. So why might I want to do that? Well, I think I sort of hopefully introduced that in a way that made sense, which is that panic.qmd is basically just an earlier commit. I just didn't treat it as a commit. I created an entire naive copy in my file system, extremely wasteful. Not a huge deal because it's 304 lines of code, right? But if I were backing up a database or something, that would be ridiculous, right? So what we're going to do is we're going to take this problem that is NP hard, which is sometimes people refer to that as intractable in their algorithms class. And we are going to make it solvable in polynomial time with the technique dynamic programming. So we're introducing dynamic programming. I had a hard time nailing down what I think is a conventional definition of dynamic programming, because this is not usually the kind of thing I would ask Wikipedia for. Simplifying a complicated problem by breaking it down into simpler subproblems in a recursive manner. I don't know. So that doesn't work because that also describes divide and conquer algorithms like merge sort. The term dynamic programming was invented by this person, Richard Bellman. No idea who that is. Never heard of them before. I'm aware of something called the Bellman operator, and I don't know what it does. Richard Bellman wrote a textbook in 1957. So that is 12 years before there were operating systems, basically. The purpose of this work is to provide an introduction to the mathematical theory of multi-stage decision process. Decision problems are like this interesting field. I think of them as being like logistics or something, right? Like, hey, we have to decide. I think of this as all coming out of the Second World War. It's like, hey, I've got this crate of ammunition, and it has to go to the front lines. Like, what is the next stop on its trip? You're like, oh, I don't know, because that's hard, right? So you have a multi-stage decision process where you're deciding something like letter routing for the United States Postal Service, right? Since these constitute a somewhat formidable set of terms, we have coined the term dynamic programming to describe the subject matter. So it's sort of like there were these problems we were solving. Some of them seemed related, some of them not. We just called the whole thing dynamic programming and moved on with it. There is a book I really like. I wanted to teach it next term, and I didn't think I could get enough students to take the class because I was going to require linear algebra, because I've been talking about linear algebra all day. If you're looking for something to do, this book is awesome. It's in Julia, and it's by money people, like finance, but it's really cool. And this teaches you all kinds of stuff about, nonlinear systems and whatever conjugate maps are, right? We should just, as humans interested in computing, we should know all this stuff. Certainly we should know Markov dynamics. I had a class on Markov chains, but now that's turned into AI and things like that, right? So Markov decision process. So go ahead and check this textbook out if you're looking for something to do. It is the textbook I would work on for fun if I were working on one right now. And so in the absence of, I think, a widely agreed upon definition for dynamic programming, I Control F to dynamic programming in the dynamic programming textbook, and nowhere does it define dynamic programming in the entire textbook, right? I'm just going to use a simple solution. I'm going to take a complicated problem, but I'm going to take the minimally complicated problem. So this is Fibonacci sequence. This is how we teach recursion. So we're going to use the recursion problem. I'm going to break it down into simpler subproblems in a recursive manner, and I'm going to do it with Fibonacci sequence. I mentioned there's this sort of tension with merge sort, because I like merge sort a lot more than the Fibonacci sequence, right? I find it much more interesting. It has implications on all of this stuff because the things you're merging are different sizes in memory. So I find merge sort a lot more interesting, but it doesn't really do the same thing that Fibonacci does, which is it doesn't have overlapping subproblems. The Fibonacci sequence, you care about the two previous elements of the Fibonacci sequence, and those care about each other. So your complexity is much higher. With merge sort, you cut something in half and then they're totally isolated until you merge them back together. And merging is basically trivial. So I'm avoiding divide and conquer. This split between divide and conquer and dynamic programming is my understanding of the text in CLRS, which is this textbook, which you might have had in algorithms. This is my algorithms textbook. And I have an algorithms credit from 2 different universities that both use this textbook. So I regard this as the authoritative text. Great textbook. I want to show you how I perceive this as non-overlapping. If I cut through the middle of my screen, that's a tree on top and a tree on the bottom. It is not a DAG. There is no arrow that goes from here over to here or vice versa. So I'm able to evenly split this, and the problems decompose down and then build back up, and there's no dependencies across any of the decomposition. Here's the counterexample, which is the Fibonacci sequence. This is a representation of the Fibonacci sequence. How so? The third element of the Fibonacci sequence is based on the first and second element. The fourth element is based on the third and second. That means both the third and fourth element of the Fibonacci sequence care about the second element of the Fibonacci sequence. The fifth cares about 3 and 4, and so on. So this is a DAG. It is not a tree. We can see there's 2 incoming edges to F2. There's 2 incoming edges to F3. And there's 2 incoming edges to F1. So this is my claim. If you can sketch out your process as a tree, it's divide and conquer. Otherwise, it's dynamic programming if you're solving it recursively. You don't have to worry too much about the DAG being acyclical, because if you write a recursive solution to a cyclic problem, it just never terminates, so you're just going forever. So don't worry about that too much. My take is that I believe and I don't know. I was not too close to mRNA when it was going. I was physically close to it. The team at UNC Chapel Hill was one of 3 big teams that pushed mRNA COVID through. I am 100% sure they were using dynamic programming over bioinformatics, because otherwise they wouldn't even call it mRNA. mRNA is just a way to carry information. The best way to understand information of that type is basically these common subsequence problems we're working on. I have newfound huge respect, actually even in the past couple years, for the U.S. biotech industry, because it's one of the few U.S. industries that has sort of stayed ahead of competitors internationally. So the United States does not have the best operating system or the best. So Nginx, which was one of the things I talked about, that was like written by like one Russian by himself after the fall of the Soviet Union when he had nothing going on. Like, I said himself. I don't know the gender of the programmer, actually. So I should not assume. And anyways, mRNA, no one else can do it, right? Like, it looks like there's other world economies, at least Russia, India, and China would spend $1 trillion on solving mRNA, and they still can't do it. So dynamic programming is a pretty big deal. Now, obviously, it's not trivial because there's people in other countries that understand dynamic programming and didn't just invent an mRNA vaccine, right? But it's a component of the tool set. So we're going to look at our toy example. We all love LaTeX. So we have I guess these are probably supposed to be on different lines. Does anyone know how you're supposed to express the Fibonacci sequence in LaTeX? Anyways, if you do, let me know, because this is probably not it. We have f of 0 equals 0, f of 1 equals 1, and then f of n equals f of n minus 1 plus f of n minus 2. I like it a little better in Rust, and let's go ahead and get it working in Rust. Actually, let's check time. I have time, right? Yeah, okay. And mvim source main. I've been changing programming languages too much today. Okay, so let's go ahead and write our Fibonacci subsequence, or Fibonacci sequence. So I'm going to create a function. It's going to be a Fibonacci value. It doesn't really matter what type of integer you use. I'm going to use a U64 because I'm most comfortable with those. You can use an I32 if you want. It's going to return a U64. And then this is like the most perfect and direct application of the match statement I've ever seen, right? Like, this is so cool. So I'm just going to return something. What am I going to return? I'm going to match n. If it's 0, I'm going to return 0. If it's 1, I'm going to return 1. And if it's n, I'm going to calculate the fib of n minus 1, fib of n minus 1, and then add that to the fib of n minus 2. Did you notice that the B is right next to the N key on your keyboard? That kept getting me there. There's like a lot of B's popping up. Which reminds me of the hit single Bees in the Trap. Never mind. Nicki Minaj, right? We love, yeah, Barbie things. Okay, all right. So then we can go ahead and we can calculate a Fibonacci number. Does anyone have a favorite Fibonacci number? I'm going to put 17 in here unless someone says something cooler. Okay, I'm putting in 17. You all asked for this. Okay. Oh, it's 1,597. I have no idea if that's correct. Let's look at a smaller one. Whoa, that's a lot of 4s. What am I doing? Okay. Oh, 3. Okay, and that makes sense because it's 0, 1, 1, 2, 3. That's 0 indexed. Okay. That seems right. Does that seem right? Okay. Let's check one more. Oh, we can just do this. Debug fib 5. Wait, did I say degub? It's debug. Okay. I'm intrigued by Rust's confidence that I'm only willing to write 3 letters for a debug statement, but that I want to write 7 for a print. I just want to ask some questions. Okay, this makes sense. 3 plus 5 equals 8. So we're doing something correctly here. You got to give credit where credit's due. The match statement is a way better way to solve this than things in like any other language, right? This is a case where the Rust solution, I'm sure that's fewer lines than you're getting in Python, unless you do something extremely unhinged like array indexing, which I do encourage. What is the time complexity of fib? Well, it's not too bad. It's a recurrence relation, so we can figure it out. If we want to calculate the value of the nth Fibonacci number, well, then we're going to calculate the n minus 1th and n minus 2th, which just means we're going to add the complexities of those together. What does that mean? The Fibonacci sequence is its own complexity. How cool is that? That made this so much easier. I was halfway through writing the computation to compute something's recurrence complexity, and I realized it was the same code, which is so cool. Also, that's terrible. Remember this one? That's really bad. You do not want to have 16,000 of anything when you're calculating the 17th value, right? It's basically O of 2n. It is much smaller than 2 to the n, but it increases at an exponential rate. So what are we going to do? No problem. We're going to use memoization. This is one of these words that's spelled differently in US English, which has a Z, and UK English, which has an S. In computing, memoization or memoization is an optimization technique. Optimization. It does not enable you to solve things you couldn't solve otherwise. It is a performance improvement. Now, it just so happens in this case, the performance improvement is going to take us from intractable, too slow to use, to fast enough to use, right? So it's important, but it works by storing results of expensive calls to peer functions. I don't think I or anyone else has taught you what a peer function is. A peer function is a function that returns the same value every time, and it does not affect the return value of any other function. The Fibonacci function is an example of this because no matter how many times I compute fib 17, I'm going to get 1597. And no matter how many times I run that, nothing else I do is going to change. So it is pure in the sense that it has no side effects, right? It doesn't update the value of an array or something. It works by storing the results of expensive calls to peer functions, which means it's no longer a peer function itself because it's storing results. So that these results can be returned quickly should the same inputs occur again. It is a type of caching, normally implemented using a hash table. It is an example of using space and time differently. So the more memory space you have for your memoization, the faster your code can run, but now the more space and memory it takes up, memory is also not free. So at some point we're going to have to pay for all of this. The runtime of a program is reduced by increasing its memory usage. I had only heard of memoization when I learned this. I was looking up memoization to make sure I was on base for this, and apparently there's a competing formulation called tabulation. I'm not teaching you tabulation. There's a link to Geeks for Geeks right there. If you end up using tabulation by accident, that's fine. So I now have my ingredients. I have a problem with overlapping recursive subproblems, and I have an array or a vector, and definitely not a hash map. I'm not using hash maps today. Hash maps are for cowards such as myself last week doing graph theory. So just don't use a hash map unless you need one, basically, is my recommendation. So I'm going to index into an array. This is going to get real annoying real quick, which is that, say I have an array fib, I think I called it fast, U64. That's going to return a U64. Okay. So say I happen to have some array already from somewhere, or perhaps a vector from somewhere, but maybe we have like let first n equals vec 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Okay. So I have the first n in my vector. Perhaps we check to see if n is less than first n dot len, then we're going to return first n. Why'd I use n for everything? I don't know. And then otherwise we're just going to throw it to do. Okay. You can't do that. That's against the law. And it's against the law because the indices of vectors and arrays in Rust are a specific type, and U64 is also a specific type, and they are not necessarily the same type. The type of an index of an array is a U size. Now, this has probably never come up because we probably usually just write an iterator and we say, for 0.m, do this over the vector, right? Now, it's colossally annoying to us because we're specifically doing the case of memoization, where we're going to use solutions to numerical problems as indices in an array. So actually, this is the hash table problem, because if I had a hash table, I could create a hash table where the keys are U64s and the values are U64s, and I could look it up in this way naively. I thought this was interesting, and I sort of wanted to deal with it. So let's fix this problem. What we're going to do instead, so we're just going to overwrite n as, let's see, n equals n as u size. Is that right? Does that look right? Does anyone know Rust? Rust people? Is that? No? Okay. We'll find out. Okay, that works pretty well. It compiles. And then we can do some other tests. Let's see. What should I do? Let's, for, is it, is that a loop? I guess I want to start at 1. Debug, fib, I. No, I want to do a print statement. Print line, and we will do fib I equals something, and then fib fast something equals something. And those will be I, fib I, and fib fast I. Okay. And so we can see we get the same values, and we can go up to higher numbers. We'll go to decimal 10. I don't know how to use Vim. Okay. And so, okay, we're getting the same values, good for us, right? Okay, so that's all well and good. And then what happens if we just go to, like, I don't know, 20? Oh no, we foolishly didn't think to make sure that we wrote down every single Fibonacci value in the universe. Why didn't we think of that? We're such silly geese. Honk, honk, right? So we need to solve this problem. Okay. So, how am I going to solve this problem? Let's do a step-by-step solution, and I will narrate the steps as we go through them. So, first thing we're going to do. I wrote fib fast, and I put some example code in here. Let's just get rid of all of this for now. Okay. So what do I need? I'm going to need, well, I have my first ingredient, which is I'm trying to solve the Fibonacci problem. My second ingredient is I'm going to need a vector. So let's just go ahead and create a vector. And that is going to be, I'm going to call it mem for memoization. It's going to be a vector of u size. And it's going to be, we're just going to start it with 0, 1. It kind of feels like cheating if I'm going to be if I am going to be comparing the performance of different implementations of the Fibonacci sequence. It very much seems like cheating to start with a bunch of them pre-computed, so I'm just going to use the same number of pre-computed values I did here. So that's the first thing I'm going to do, and then I'm also going to let n equals n as u size. I'm just going to switch things over to u size. It's a little bit cheating to just use u size here, but here's the thing. U64 was already chosen arbitrarily. So I have to decide some size of number at some point. So I'm going to do that. And now I'm going to make a helper function. Why am I making a helper function? Well, somehow I need to keep track of my memoization array. And in order to have my memoization array while I'm computing different Fibonacci values, somehow I have to move that memoization array around. Now, if I were writing our most beloved language, Python, I would just throw it in some global and update it all the time, right? We're not really supposed to do that in Rust, so we're not going to do that. We're going to write an internal function. So I'm going to call this thing inner. You can call it whatever you want. Wait, what is going on? I thought it was in insert mode. Okay, inner. I'm just going to name the variables differently that helps me keep track of things. So I'm going to have an x, which is a u size, and I'm going to return a u size. This is also going to get a to-do. This inner is not sufficient. It's going to need other stuff. So how am I going to solve that problem? Well, I'm also going to need to pass around my vector. This vector is the memoization array. This is what I'm going to use to store my results. And in order to not have scandals with, ownership, I'm going to pass it around as arguments and return it as return values. So I'm going to get a mutable vector of vec. Also, I should say this to be clear about it. I have absolutely no consistency on where I put my spaces. That's because I don't know Rust. So what I'm going to do is I'm going to finish writing this line, I'm going to exit, I'm going to cargo format, and then we're going to open it up again. Okay. I'm going to have a vec of usize. And then I'm going to return a usize and a vec of usize. And it doesn't fit on the screen, which is sad. Okay, I'm going to make this big, and then we're going to look at white space. Okay, so I have spaces on both sides of a colon here. I have spaces on neither side of a colon here, neither side of a colon here. Save and exit, cargo format, source main, and it standardizes all of them to having colon adjacent to the alias or the variable name, and then spaces elsewhere. Okay. So now what I'm going to do. I am going to, within inner, I am going to compute some return value. Oh, there's some way to do multi-line here, right? Is that allowed? No, that's not allowed. Okay, I got banned for that. Okay, so what am I going to do? I'm going to compute some return value, which is going to be a usize. If x is greater than the length of m. What is m? M is the memoization array. If x is greater or equal to the length of m, it means that I have not yet computed the value for that Fibonacci number. So I'll have to do something. But otherwise, I can just say, oh, the return value is going to be the x value in m. And then I can simply return the return value and the memoization array. Okay? I'm also going to finally update my return statement now, because now I know what kind of thing I'm getting back. I can return. Inner just computes the Fibonacci sequence, but it computes the Fibonacci sequence and returns two things. It returns the memoization array and also the value. I only care about the value. So what am I going to do? I'm going to compute the inner of n and of m, my memoization rate. Why did I call it m and m? Mem sounds like a letter. I should have called it r. No, that's also a letter. I don't know what I should have called it. It's the memoization array. Okay. So I'm going to have n and m. I'm going to get the first value in that tuple that I return. So this is a tuple. It's also a tuple. And I just want the ret. I want the return value. And then I have to turn that back to a U64 or the code explodes, but watch this, we can check. Is my code going to explode? Yes, that is not allowed. I need to, excuse me, I have to return a U64. And I guess there's also some error in line 17. Oh, this is supposed to be ret equals. Okay, so we have that. And then all we have to do now is deal with the recursive step. By the way, you may have noticed that this is more code than the slow solution. Correct. So we are going to recurse. If x is greater than or equal to the length, then we call inner on x minus 1 and the memoization array. We're going to save the results of that computation, but we actually don't care about the x value that comes back. That just doesn't affect our daily lives, because we're only going to update the memoization array. You can capture the x value if you want, or it doesn't really matter. And then what are we going to do? Once inner has returned, that means you have successfully computed the Fibonacci values all the way up to x minus 1, which means you can compute them for x. So what are they for x? What? I keep entering insert visual block mode, and I don't know what I'm pressing. Okay, so m of x minus 1 plus m of x minus 2 is equal to the current Fibonacci value, and I know that those values exist because I just computed them, right? I'm going to set that equal to the return value, okay? I'm going to close this, and then I'm also going to cargo format that because I don't know if I'm supposed to have spaces here, right? Cargo format, cargo run. Okay. Oh, I didn't solve my casting problem. This is as u size, or as u64. Okay. Cargo run. There we go. Look. Oh, we did it. We did it. We're calculating values. There's only one teensy tiny little teeny itty bitty problem, which is that this code explodes instantly if you ask it for the second Fibonacci number. No, that's not true. We can get two of them. You cannot ask for the third one. Why is that? Well, I'm never actually adding anything to the vector. So what I need to do is I need to take this ret value, and I also need to throw it onto the end of the vector, which I think is m dot push ret. Let's check the answer key. It is! Yeah! I'm a genius. Wait, did I cargo format? Sorry, I want to see what this looks like. We'll just cat it. Okay, so with cargo format, you get spaces around your mathematical operators. It still allows you to write this, which I think should be broken up into multiple line. And then we have m push ret. Okay, I'm sure this will work this time. Okay, so I was not sure it would work, but it did. So good job us. Sometimes you just got to count your chickens before they hatch, right? Usually you'll know how many chickens there are. Let's slow this down. Yeah, let's go to 40. No. Oh, I did double R. I see, okay. Okay. Surely this will be fine. And do you notice how it slowed down there? Here, I'll run it again. Ooh. Ooh, that's not good. Folks, that's straight up bad is what that is, right? And I know what you're thinking. You're thinking, Professor C, the big C, as they call me. You don't have to start calling me the big C. Did you want to write down that you don't have to call me that? I know some of you are taking notes. Okay, that's fine. You can call me the medium-sized C. That's fine. Like replacement size C. I'm about average in most respects. Okay. I know what you're thinking. You're thinking C of approximately expected size. So I guess that would be like the Aegean Sea, right? You'd be like, Aegean Sea, all you've just demonstrated is that somehow you're bad at writing code. You haven't even demonstrated which code is bad. And I agree. I agree completely. So, first of all, the first step is admitting you have a problem, right? So we'll just comment this line out. We'll yoink it. That's not, let's see. How do I yank point? There we go. I'm only going to print fib this time. And we'll see if it's still slow. And we'll go to 50 so we have more time to look at it. Okay. Folks, I'm thinking the Fibonacci computation is a little bit slow, right? Do you know how much Bitcoin I could have mined while doing this instead, right? And this is only performing additions. This isn't even doing anything exciting. Like, it's completely ruined at 43, right? And that's not a big number either, right? Like, this is, how many zeros that thing got? That's like, there's countries with more people than that in them, right? I know what you're thinking. You're thinking you still haven't demonstrated that the fast version is better, right? Okay, it's a little bit better. Sorry, do you want to see that again? Oh, it's going about as fast as it can print. That's memoization, folks. Huge W for memoization. But we should investigate this a little bit further. Okay, so here's the side by side. I'm showing you them side by side so you can see that there is really a heinous number of lines of code in the memoized example. I just don't think there's a way to make your code short and concise while doing this, and that's okay. Obviously, it could be shorter in Python, but then you're dealing with like memory problems, right? And so it might explode. Let's go ahead and actually write an interesting testing script rather than just dispatch things this way, which I've already done. Let's actually conduct some analysis, and I want to introduce a sort of final novel concept today. This concept is inspired by class today. It's not necessarily required, but I'm going to introduce code analysis through instrumentation. And what do I mean by that? Well, when we talk about time complexity, oftentimes we just like say big O of something, and we don't say big O like what big O is. And so what I'm going to say is I'm going to claim the expensive operation here is plus. That is a lie. The expensive operation here is return. But that doesn't matter because we plus and return in the same place. And separately, if I were really good at writing code, which we could sit here and just do it quickly, right? We would be able to take out all of those return functions and not write any of this recursively. We could change it all to iterative, and then the returns wouldn't be the limiting statement. Anyways, we'd go up to like 60 or something, right? Because again, the performance is half as fast every single time we double, so it slows down a lot. We're going to get a little bit of performance from that, right? But we're still fundamentally going to be adding additions to the mix. So our complexity is addition complexity is the claim I am making. When you do merge sort and quick sort, the complexity, what you're getting charged for there is comparison. What is the complexity with respect to comparison? So I'm going to add instrumentation. I use instrumentation in my research, and I use it at this level. Because if you're trying to see if there is some secret over here, and you're trying to see if it gets to over here, one of the ways you can simplify this is you can make a much smaller design that only has a single bit at each place, and the only thing those bits say is, yes, I saw what was in there. This is instrumentation, and it is much cheaper than doing lots of other things. It is a relatively cheap way to study designs. So I'm going to add instrumentation to my design, and I'm going to do so that we can see how many additions are performed. I'm just going to dump everything to the sort of command line output, and so how am I going to do this? There is only one addition in fib. It is at this line, so I'm going to add a print statement to this line, and I'm going to do that by extending this expression. I'm going to open an expression block with curly brace. I'm going to print something. I'm going to print that this is the slow version. I'm going to terminate my expression with a semicolon, because it's the end of a thought. I'm going to come down here and I'm going to get rid of this comma. We can see the comma's missing over here. There's no comma there. Why is that? The expression which doesn't have a semicolon at the end is the return value of the expression. So essentially, this code block will have the same value as this expression. This expression itself doesn't need a comma at the end of it because it is the outer expression, this one, that needs a comma at the end because that's what we're matching to. So we're matching to this entire statement, and we're only taking on the value fib n minus 1. Maybe that didn't make sense to us. That's OK. Watch this. We can run it. Oh, we're not showing it right now. This is going to say slow a whole bunch. It's going to say this millions of times. Billions, actually. But there you go. See, it's showing up. That wasn't particularly helpful. Not to worry. What if we just go to 5? And that's not too bad. That's showing you how many additions you're getting every time. We can do the same thing with the inner function. Why would I instrument inner and not fib fast. Well, they're kind of the same thing. But where does the addition occur here? So if I just search for the addition, there's only one. All of the computation of fib fast is taking place also in that same single addition. Now, fair play, if I'm saying additions are expensive, probably subtractions are expensive, and I'm doing a whole lot of subtraction in here, right? But, oh, by the way, doing a little bit of subtraction up here too, so that's probably fine, right? In all of these, we only ever refer to this sum, n minus 1 and n minus 2. So all of those are the same. So I'm going to instrument right here. In this case, I'm already inside just an if statement. To me, memoization felt shockingly un-Rust-like because it sort of pushed me into writing these if statements instead of these match statements. I don't know that that's true. I guess you could match on this Boolean value. I don't know. So like maybe there's a more rustic way to do this, and I don't know what it is. There's also languages that memoize by default. So I learned Racket and Common Lisp, and those just store the result of everything somewhere, and you just never find out, and your code's just fast, and you don't know why. So look out for that stuff. This one's fast. That didn't change, and then we go down here. Let's go up to, we'll go to 10. I always forget that 10 has more characters in it than 1, because it just doesn't feel like it should. Okay, I guess I could have put an A there. Okay, not too bad. And then, is this bad? Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8 additions to calculate fib 9, or there are, it's off the screen, it's a whole bunch. There are many to find fib 9. And in fact, by the way, there's 34 of these, which you can tell because of that. That's the 34. We're only adding one together. Okay, so we can compare them in such a way. Let's do a little more work into this. I'm going to additionally configure main to accept a command line argument. Why is that? Increasingly, I expect at this stage in the semester, you're going to be wanting to basically write testing harnesses for your code, and usually I do that by just like writing things in command line. Frequently, I actually write a Python function that dispatches a bunch of cargo runs. Like you can do whatever you want. And you saw this with IX when I gave you a testing framework. You can use Cargo Bench for this apparently, but then I think you have to cargo install Cargo Bench, and it's like a whole thing. So I just wrote code because I know how to do that. And so here's what I wrote. And let's go through the thought process here. Wow, my voice is so cooked. Oh, if you want to know Cargo Bench, I suspect if you just mention it to Jimmy on Wednesday, you will learn about Cargo Bench. We were collaborating on something, and he wrote like a test suite for it that didn't run on my computer because I had an older version of Rust C, so I deleted it, but he was really proud of it. Okay, so main. I'm going to get some arguments, which is going to be a vector of strings, and I'm going to get them from standard and args. I guess I don't even have to collect these, do I? Yeah. Standard env args gives you an iterator, so you would call next on it. I'm just going to collect it all into a vector because I want to see how many of them are. So I'm going to collect that into a vector. You could call me the colvector. Okay, that one wasn't that funny. That's okay. I'm going to check the length, and I need the length to be 2 because I'm going to provide 2 arguments. I'm going to say how many fib I want and whether I want fast or slow. So I'm going to let n, which is a U64, be the 1th argument. Why is it the 1th argument? The 0th argument is the name of the executable. So I'm starting at 1. I'm going to parse that, and I'm going to unwrap it. Now, if I didn't put 64 here, parse would not work because Rust would not know what to parse it into. So we're going to leave that out and we'll fix it. Whoops. Okay. And then, okay, I can't even leave comments here. Okay. I am just going to dispatch either fast or slow. So I'm going to set nothing equal to match. Oh, I think, let's not put that there. We'll see why we have to do that. args2. I'm going to get the characters in the string. And I'm going to take, so the characters is going to return an iterator. I'm going to take the next, which is the first, because I haven't taken anything else from it. And I'm going to unwrap that. Why is that? If there's not 2 arguments, there isn't a first character, so I know there's something there. I could write expect, but I'm just going to write unwrap. Okay? What am I going to match that with? I'm going to match that with f for fast, fib fast of n, and then s. Do you think those are the right quotes? I think those are the right quotes. It's single quotes because we're matching a character. Fib of n. I have another statement there, but like these are the only things I want to match. And then we'll return. Okay. So this code won't work, but let's look at tail source main. Okay. So this is what my main looks like. Let's go ahead and try and cargo run that. And I'm going to provide it some arguments. I'm going to look at the 10th value fast. Okay. Why does this not work? This statement is not surrounded by a body. Oh, it's the semicolon's missing. Okay, that's reasonable. So inside match statements, I end my lines with commas because they're different possible outcomes. Outside of match statements, I end my lines with semicolons because they're complete thoughts. Do I know how Rust works? Absolutely not. Okay, what's going on here? Patterns. What are not covered? Oh no, I see what's happening. Sorry, I'm portraying a character right now. The character is me. This could be a lot of stuff. And I'm saying it just can be F or S. I should deal with other cases. That's reasonable, Rust. Thank you. And that is what you call a Rust W. So if I see anything else, what am I going to do? I'm going to instantly panic. I love to panic. And by love to panic, I mean I love to panic, comma, not panic, semicolon. I think it's very cute that the Rust programming language thinks I have any idea if I'm in a match statement or not when I'm writing code. I'm living in the moment. I don't know. Okay, so there we have some fast, and there we have some slow. That's kind of cool. But that's not like quite scientific yet. So how am I going to solve this problem? Well, I was going to use word count. Word count is a cool thing. You can use it to count words. I'm teaching a class that has a writing requirement in it, and there's many students that are claiming they don't know how to count the words in their assignments they turn in. I was a little skeptical of that, so I just taught them about word count. They seem less happy than they were before I taught them that. But anyways, so we can go ahead and do some word counts. And one thing we can do is if we cargo run this, we can throw this into slow.txt. And then we can word count slow.txt. And that's kind of cool. That's a little bit cool. But wouldn't it be way cooler if we didn't have to write that file? So let's get rid of that file. And let's instead cargo run 10s. And I'm going to do a pipe. And I'm going to take the output of cargo run 10s. That pipe's going to mean to take the arguments and provide it to the next command. And I'm going to do a WC command. And it's going to give... WC stands for Willamette College. It's named after this undergraduate program. A lot of people don't know that. Some people think it stands for word count. That's fake. It's named after Willamette College. Okay, so that's an 88. And then how much complexity do we have for fast? We have 9. That was still kind of like, you know how there's like a lot of gibberish on my screen here? And in fairness, like I'm the one that cut my screen in half, but that's kind of long, right? So I'm not like a huge fan of that. So what if we write a little more sophisticated script? And I'm going to run both of these at the same time, and I'm going to capture some stuff. So I'm going to cargo run 10f. Then I'm going to semicolon. Oh, semicolons in bash. It's the same thing. It's ending the thought. Then I'm going to cargo run 10s. And we can just run those at the same time and see what happens. We can also take both of those and pipe them to Willamette College. There's no way any of you call it Willamette College, right? What do you just call it, Willamette? But then people might think you're referring to us and also the law school. Okay, so this is still super annoying because Rust is talking to me. And as I always say to computers, how dare you speak to me, right? So we're going to take the computer, and it turns out this stuff here, that is going to the error stream, which is different than the output stream. The error stream's name is 2, and the output stream's name is 1. So we're going to take 2, and we're going to direct it to dev null, which is also known as the shadow realm. And then we're just going to see the word counts directly. And that's kind of cool. It might be the case that we can get just the lines. No problem. We're clever. I think. We'll see. Maybe this will explode. And that's a way to do performance comparisons. So we can go ahead and come in here and we can do like 30 or something. That might have been a bit much. But this is one way to use instrumentation and test your code without using Bench or whatever else people are using. Okay. I ran this trying to get 40, and I ran it over my lunch break yesterday, and I got this result. So we were millions of times faster. But we can do something a little bit easier, which is we can echo the mathematical result, which I guess you do just 2 parens, and we're going to take 134,628 divided by 29. Do I have to put like a dollar sign there? No. How did I do this? I was for sure that was going to work. Oh, there's just an extra paren at the end. So when I'm computing the 30th Fibonacci value, the memoized version is already 4,642 times fewer additions than the other one, which is pretty big. And it doesn't show up that quickly. Like, it's pretty low at 10. What's this going to be? Oh, that's just 10x, right? So it's 10x faster at 10, 4,000x at 30, 4 millionx at 40, and this is just the exponential split that we're used to seeing. Okay. You can also just time it. Once things slow down enough, you can time them. So we can time cargo run 40f. Oh, I should turn off the prints. Does it matter? Okay. Is this going to work? Okay, I think that's fine. And then slow is... Why'd I do 40? I know this is going to take forever. Okay, we're going to do 30. You start seeing the time split here. So that's 40x slower. Note, 4,000 times as many additions, only 40 times slower. So something else is slowing us down. And let's take a look at 20. And at 20, you can't even really tell yet. You're not doing enough computation time to actually effectively measure anything. Why am I pointing this out? Something you should say when I start memoizing is, of course you have to do less computation, but what about all the memory costs? Isn't it costing you a ton of time to make and pass that vector around and all these things? Yes, it is. It is slowing the code down a lot. It is just not slowing the code down nearly as much as an intractable problem. So when I'm passing that array around, yes, it is slowing me down, right? It's slowing me down a lot. But I'm still way faster than not doing it. So, 24x speed up with memory costs. And what was the speed up here? It was 4. It's faster. By the way, here is a fun challenge problem. Exactly how much memory is used by this call? And you can calculate it in terms of bits, right? This is going to calculate the 40th Fibonacci sequence. I already have to save the first 2, no matter what. And I don't have to save the 40th one. I'm returning that, which means I have 37 other values. This is 37 U sizes. I don't know how big U size is, but I'm assuming it's a U64, and I could have converted everything back and forth into U64s if I had to. So that's 37 U64s. Give me my number thing. It's that many bits. So it is 2 kilobytes. I can calculate some pretty big Fibonacci numbers before I'm using an appreciable amount of memory, right? If I get 1 megabyte, I can calculate 1 million of them, right? So it's just not that expensive to memorize this stuff. This is the code for today. It is easier to see not on the slides, but if you go to home, and then you come down here. I'm trying new ways to embed this, and this is an embedded gist, which might be a little nicer. So there's not a copy-paste block. Okay, fair. But it is hosted directly, so you can curl it. So depending on what you want. No, okay, curl main.rs. Oh no, I got a thread panic. Okay, well, we tried. Oh, that means I just destroyed everything I did in class today. That's kind of sad. Okay. And then we did all of these things today. Good job. Okay, I'm going to just do a quick overview of the homework and then let you go. This homework is cool. I think you'll like it. And I think it will make sense to you now, but I'm not sure. It's going to be 2-dimensional dynamic programming, and I just taught you 1-dimensional dynamic programming. It's the same thing. Don't worry about it. Everyone always confuses me with Vin Diesel, so I want to show why, right? And the reason is if you create a table and you put Calvin, and you can put my whole last name here, but there's no reason to do it, and you put Vin Diesel on the other way, you can see that there's some letters that line up. So, for example, we both have a Vin substring. So how are you going to do this? You start at the top right, and you put zeros everywhere. The letters don't line up. But then if you ever see a letter lines up, so I'm sort of snaking across here, you can think about how you're going to do that procedurally, right? If the 2 letters are the same, that means you have a common subsequence of length at least 1. So that means there's a 1 here. So if they're the same, you add 1, and what do you add 1 to? You add 1 to the previous substring, which is up here. Now, if they're different, then you just keep the ones going, but if they're the same, you increase the size of the substring. So if we have Calv and Vin Diesel, our longest substring is of length 1, but if we have Calv and Vin Diesel, our longest substring is of length 2, or subsequence. I shouldn't be saying substring. Substrings are different things. When I say LCS is not to be confused with LCS, one of them is longest common substring and one of them is longest common subsequence. I did not know these things were different until I started writing the code. And in fact, you would calculate them the same way. Okay, so we see there's this sort of vertical where values increase until around here. And then they increase again down here, and that's because Diesel has DIE and I just have DE. So when you expand all the way to Calvin DE, if you only have Vin die, then you don't have a longer substring. So, subsequence. This is the subsequence. Here's a template to work with. And there is also a really good worked example on Wikipedia with arrows. So I think you'll figure that out. I think it'll be pretty fun. I don't think this is like an unmanageably hard homework, but it is very, very cool and useful. Especially if you haven't done dynamic programming before, which I think maybe you haven't. So take a crack at this. You definitely don't have to start that now because you still have analysis going on, but I don't think analysis was hard. So maybe. Anyways, be nice to Jimmy on Wednesday and ask good questions and tell your friends that aren't here today to turn up. Thank you so much, and yeah, have a nice week. What are we doing next week? Merkle, right? Whoa! Look, it's a merge conflict! That's so cool! Wow. it's like a meta comment